Hey everybody, I just wanted to come really quickly and share the story that I found to be pretty intriguing. Not sure if you guys are into much of the, particle physics stuff, but it always intrigues me, and I wanted to come and let you guys know about the W boson, how they say that it's heftier than anyone expected it to be. And so I just wanted to take a few moments and just read this with you guys because I'm not sure if you all know that just recently they were doing a lot of different testing with CERN, and they're about to start that particle, that big, collider up very soon, for it to run for about a year, right? I may be wrong. It could be just a couple of months, but I know that it's supposed to go for a little while. So whether they're running it continuously, which is going to be some magnetic for you, or whether just doing it for a short time. But this affects the standard model, the story right here. And you can see it right here. It says an ultra precise measurement of the mass of a subatomic particle called the W boson may diverge from the standard model, a long reigning framework that governs the strange world of quantum physics. After 10 years of collaboration using an atom smasher at Fermilab in Illinois, scientists announced this new measurement, which is so precise that they liken it to finding the weight of an 800-pound gorilla. Get this, to a precision of 1.5 ounces or 42.5 grams. Their result puts the W boson, a carrier of weak nuclear force, at a mass 7 standard deviations higher than the standard model predicts. That's a very high level of certainty, representing only an incredibly small probability that this result occurred by pure chance. Now, Joe Lycan, Fermilab's deputy director of research, said in a statement, quote, "While this is an intriguing result, the measurement needs to be confirmed by another experiment before it can be interpreted fully." Now, the new result also disagrees with the older experimental measurements of the W boson's mass. It remains to be seen if this measurement is an experimental fluke or the first opening of a crack in the standard model. That's the part that I found to be intriguing. So it says that if the result does stand up to scrutiny and they can be replicated, then it could mean that we need to revise or extend the standard model, possibly with new particles and forces. That's amazing. Oh, to me, it's amazing. Anyway, it goes on to say that the weak nuclear force is perhaps the strangest of the 4 fundamental forces of nature. It's propagated by 3 force carriers known as bosons. There's the single Z boson, which has a neutral electric charge, and the W positive and the W negative bosons, which have positive and negative electric charges respectively. Because those 3 bosons have mass, they travel more slowly than the speed of light and eventually decay into other particles, giving the weak nuclear force a relatively limited range. Despite those limitations, the weak force is responsible for radioactive decay, and it is the only force besides gravity to interact directly with neutrinos. Now, those neutrinos are the mysterious ghost-like particles that flood the universe. I mean, they're everywhere all the time. Isn't that a trip? The next paragraph goes on to say that pinning down the masses of the weak force carries a crucial test of the standard model, the theory of physics that combines the quantum mechanics, special relativity, and symmetries of nature to explain and predict the behavior of the electromagnetic strong nuclear and weak nuclear forces. It says here, yes, gravity is the elephant in the room. The model can't explain, and you guys know that they cannot explain gravity at all. My question is this going to be like what they did to gravity and say, well, we just don't know, we don't have an answer, or they're going to keep doing the test to tell us what's really going on? Listen to this. It says the standard model is the most accurate theory ever developed in physics, and one of its crowning achievements was the successful prediction of the existence of the Higgs boson, a particle whose quantum mechanical field gives rise to mass and many other particles, including the W boson. According to the standard model, at high energies of electromagnetic and weak nuclear forces combine into a single unified force called the electro-weak interaction. But at low energies, or the typical energies of everyday life, the Higgs boson butts in, driving a wedge between the 2 forces. Through that same process, the Higgs also gives mass to the weak force carriers. If you know the mass of a Higgs boson, then you can calculate the mass of the W boson and vice versa. For the Standard Model to be a coherent theory of subatomic physics, it must be consistent with itself. If you measure the Higgs boson and use the measurement to predict the W boson's mass, it should agree with an independent direct measurement of the W boson's mass. You see how that works? Using the collider detector at Fermilab, which is inside the giant Tevatron particle accelerator, a collaboration of more than 400 scientists examined data for years. It said examine years of data from over 4 million independent collisions. Who knew? Who knew? 4 million independent collisions of protons with antiprotons to study the mass of the W boson. During those superenergetic collisions, the W boson decays into either a muon or an electron, along with a neutrino. The energies of those emitted particles are directly connected to the underlying mass of the W boson. Here's a quote. The number of improvements and extra checking that went into our result is enormous, said Ashutosh V. Kotwal, a particle physicist at Duke University who led the analysis. He continues, or she continues, I gotta check and see if that's a girl or a guy. Anyway, they continue with, we took into account our improved understanding of our particle detector, as well as advances in the theoretical and experimental understanding of the W boson's interactions with other particles. When we finally unveiled the result, we found that it differed from the Standard Model prediction, closed quote. The CDF collaboration measured the value of the W boson to be 80,433 positive 9 mega electron volts per c squared, which is about 80 times heavier than the proton and about 0.1% heavier than expected. The uncertainty in the measurement comes from both the statistical uncertainty, just like it says here, I found this cute, just like the uncertainty you get from taking a poll in an election, and the systematic uncertainty, which is produced when your experimental apparatus doesn't always behave the way that you designed it to act. They got a great little sense of humor, right? It says achieving that level of precision of an astounding 0.01% is itself an enormous task, like knowing your own weight down to less than a quarter of an ounce. Here's another quote. Many collider experiments have produced measurements of the W boson mass over the last 40 years. The CDF co-spokesperson, Giorgio Chiarelli, a research director at the Italian National Institute for Nuclear Physics, said in a statement. Well, they continue with, these are challenging, complicated measurements, and they have achieved ever more precision. It took us many years to go through all the details and the needed checks, close quote. The result differed from the Standard Model prediction of the W boson's mass, which is 80,357 positive 6 mega electron volts per c squared. The uncertainties in that calculation, the positive, comes from the uncertainties of the measurement of the Higgs boson and other particles which may be inserted into the calculation, and from the calculation itself, which relies on several approximation techniques. The differences between the results aren't very large in an absolute sense. Because of the high precision, however, they are separated into 7 standard deviations, indicating the presence of a major discrepancy. The new result also disagrees with the previous measurement from the other collider experiments, which have been largely consistent with the Standard Model prediction. It's not clear yet if the result is caused, this is the part that's amazing. It's not clear yet if the result is caused by some unknown bias within the experiment or if it's the first sign of new physics. The CDF result holds up and other experiments can verify it. If it does, if it holds up and other experiments, like the guy said at the top, can verify it, it could be a sign that there's more to the W boson mass than its interaction with Higgs. Here's the deep part. Perhaps a previously unknown particle or field, or maybe even dark matter, is interacting with the W boson in a way the standard model currently doesn't predict. Now remember, who was it that said they're going to mess with something and they ain't going to know what they're doing? You guys remember who that was. But the last paragraph says that nonetheless, the result is an important step in testing the accuracy of the standard model, said CDF co-spokesperson David Toback, a professor of physics and astronomy at Texas A&M University. He says, quote, "It's now up to the theoretical physics community and other experiments to follow up on this and shed light on this mystery," he said. I'm trying to remember the guy's name who said, I think it's Stephen Hawking. I know it's Stephen Hawking. Stephen Hawking said, you going to open up something and you ain't going to know what you're doing. There's a few other amazing stories here. Physicists cracked unsolvable 3-body problem using drunkard's walk. Otherworldly time crystal made inside Google quantum computer could just change physics forever. And I found that story to be very unique as well. This was last year, though, September 14th. The other one that we just got the reading was earlier this month. The crystal is able to forever cycle between states without losing energy. Look at that. That's the time crystal, and it was created inside of Google's Sycamore chip, which is kept cool inside their quantum cryostat. You guys should read this one. I'll leave this one down below too. Researchers working in partnership with Google may have just used the tech giant's quantum computer to create a completely new phase of matter, a time crystal. Look at it. Oh, this is amazing. The ability to forever cycle between two states without ever losing energy. Time crystals dodge one of the most important laws of physics, the second law of thermodynamics, which states that the disorder of entropy of an isolated system must always increase. This bizarre time crystal remains stable, resisting any dissolution of randomness despite existing in a constant state of flux. Oh, you guys got to read this. You got to read this. I'm not going to read it right now, but this is amazing. Here, I'm going to read this last little bit so it'll get you intrigued. According to a research article posted in July 25th to the preprint database, ARXIV, scientists were able to create the time crystal for roughly 100 seconds using qubits, quantum computing's version of the traditional computer bit inside the core of Google's Sycamore quantum processor. You guys, there's a lot of stuff that's going on that I think we really need to keep our eyes on. You know what I mean? We really need to keep our eyes on it. Yeah, look at this. The second law of thermodynamics says that all systems evolve toward a state of more disorder, where energy is shared out evenly across the system. Y'all, check the story out. Listen, you guys, I appreciate you all for being here. These stories both came from Live Science, and they will both be down below in the description so that you are privy and you can use it for yourself. All right, you guys, I want you all to remember what I always say on any Felicia Lockhart publications, and that is that man shall not live by bread alone, but every word that proceeds out of the mouth of the Most High. You guys see, we really do need to lean on the Father a whole lot more, right? They don't even know what gravity is. They don't even know that it's not even on the standard model. That still blows my mind. After all the years of knowing that, it just blows my mind. Anyway, you guys, I want you guys to remember that we are sponsored by MyPillow, and you can use promo code FEFE, F-E-F-E, when you call 1-800-656-1592, or when you go to their website, plop that code right in so that you can get a great discount and an even bigger discount. If it's your first time, you'll get some free goodies and you'll get an additional $10 off when you click that little button in the lower left-hand side that says $10. All right, you guys, y'all take care of yourselves and take care of one another. And until we see each other again, please continue to be blessed. All right? Okay. See you soon. Bye.
Lockhart Perspective.